Combinations, a selection of items without regard to the order. Now, this is given by n choose r, which is n factorial by r factorial into n minus r factorial. To understand, consider this simple experiment. Consider three balls and how many ways we can choose a single ball out of this. Well, you can choose the first one or the second one, or you can choose the third one. So there are three ways to choose a single ball. Now you can repeat the same and try how many ways you can choose two different balls. And you would again find that there are only three ways to do such a task. This is how we introduce combinations, and this kind of problems can be solved using binomial coefficients and combinations. We just saw how to do combinations with the example of three balls. Now let's illustrate the concept more clearly here. So say you have n objects. Let's say you have an object A1, object A2, and all the way up to object AN. So these are your n objects. Now, the number of ways, if these are distinct, the number of ways to choose any R of them, as you saw, is given by n choose R. This is called the binomial coefficient, and its definition is n factorial upon R factorial into n minus R whole factorial. We also follow the convention that 0 factorial is 1, and also negative factorial of any integer is 0. So any integer basically. Okay. So these are the conventions that we follow. And with this, we simplify our rules of combination. So there are some properties of binomial coefficients, the basic ones which we should know, like NCR is always equal to NCN minus R. This is one of the important properties that we use. Another one is N choose R is 0 if N is less than R, and this can be derived from common sense. So we will try and derive a few binomial coefficients on our own so that we are comfortable in finding the values. So let's start with 5 choose 2. 5 choose 2 can be derived like 5 factorial divided by 2 factorial into 3 factorial. If you were to do this and find all the values, you would get 10. But there is a simpler way. Whenever you have n choose r and you want to find out the value, you simply go from n into n minus 1 and all the way up to n minus r plus 1. You go back r items, basically there should be r consecutive integers starting from n going backwards and divided by r factor. So for example, the same 5 choose 2 now becomes 5 into 4, so 2 consecutive integers divided by 2 factorial, which is just 20 by 2, which is 10. So this is the simple way to do combinations, and we're going to solve a lot of choosing problems. But remember, in combinations, we do not take care of the order. So A, B, C, this is same as A, C, B in combinations because it's like multiplying. When in multiplication, these three variables will result in the same thing than in ACB. The order will not matter, but it does matter in permutations. And when that does happen, we simply multiply it using the permutation thing. Let's say you have three items, A1, A2, A3. So you can choose any two of them in 3C2 ways, right? And you are also required to, let's say, consider the order. Then those two items itself can be arranged in 2 factorial ways, and you multiply the 2 factorial with this. This is also known as 3P2, but I usually use the 3C2. And whenever required, you can simply use the factorial to multiply and denote the order. Okay, let's get back to the next one. Now let's look at some properties and identities of the binomial coefficient and combinations in general. So you have the binomial coefficient n choose r, and you know that this is defined as n into n minus 1 and all the way up to n minus r plus 1. So it is basically a product of r consecutive integers divided by r factorial. Since n choose r is always an integer, you can derive from this that the product of any r consecutive positive integers is always divisible by r factorial. And this is a very useful result that is often given to prove in either combinatorics or number theory papers. So you should try and understand this. Well, this can be proved directly from binomial coefficient, but you can also prove it otherwise. I would like you to try the other ways. Great. So let's try and reduce some of the identities. So the first thing that we know is n choose 0, the basic ones. This is equals to 1. So anything choose 0 is 1 by definition because 0 factorial is 1. N choose 1 for any n, integer n I'm talking about right now. N choose 1 should be n. And n choose 2, shortcut is n into n minus 1 by 2. It is good to remember it by heart. So this 3 would be used more often than not. So that is why you should understand these values very clearly. Now, some basic identities include, if we were to sum all the binomial coefficients like this, n choose 0, n choose 1, n choose 2, and all the way up to n choose n. So NCN, and we are not going up to NCN plus 1 and stuff, because we have already discussed that if R is greater than N, then this value becomes 0. So technically you can write that this sum goes from 0 to infinity, but still it would basically mean that it is up to this point where NCN is found. This value equals to 2 to the power n. Well, this is an easy task to prove it using identities. Specifically, you should use the binomial theorem on 1 plus x whole to the power n. And since this expands like this into 0 plus nc1 into x plus nc2 into x squared, and it goes up to ncn into x to the power n. Putting putting x equals to 1 in this equation gives you the required answer. But I would like you to try and prove it combinatorically, that how 2 to the power n is achieved. To do this, you have to assume two different scenarios and match them. That is one way to get this, and another way to get the same thing. And you would have to show that both of them also equal 2 to the power n. The hint should be power sets. Okay, let's try and find out some more identities which we can use later on. So in problems, another identity that is used is NCR plus NCR minus 1 equals to N plus 1 CR. This is a very common and useful identity, and you will find it in many JE papers and also competitive examinations, giving problems based solely on this identity. This is a very important identity, and you can try and prove it. So this identity will help you to understand how to do the manipulations between factorials and how to make LCMs and then simplify them and find out the resulting answer. Always try to force the resulting answer in your simplifications. In that way, what happens is whatever left out should be equal to 1. So if you were to force after simplifying the actual definition of n plus 1 CR in factorials inside your thing, inside whatever you got, then whatever rest happens, that is doomed to cancel out, right? Okay. So this is an important property. And then again, we have a few other properties, like if you were only to add up the even numbers like n choose 0, n choose t, n choose 4, n choose 6, and let's say we go up to some point until it becomes 0. This is equals to 2 to the power n minus 1. And similarly for the odd powers, n choose 3, and so on. This is also equals to 2 to the power n minus 1. And there are many other identities that we can prove in combinations, but rest everything is done using logic. Whenever you have combinatorial problems of choosing committees or choosing persons, everything would be done using simple logic. The fundamental counting principle, also known as the multiplication principle. Let's try and understand with an example. So we are given three different pizzas and we have four different toppings: strawberry, chicken, pepperoni, and pineapple. How many ways to choose toppings for the pizzas? Well, you can choose the first pizza and use all the different four toppings in order to get a topping on the first pizza, right? Because the pizzas are independent. In a similar way, you can also choose the second pizza and get four ways again. So, four ways to choose toppings for pizza 1, four ways to choose toppings for pizza 2. And in a similar way, you can also see that the number of ways to choose a topping for pizza 3 would also be 4. And using the multiplication principle, we would understand that if four ways are there for choosing toppings for each of the pizzas, then similarly, we can multiply them to get 64, which is the total number of ways to choose toppings for all three pizzas. Let's talk about the multiplication principle. So in the multiplication principle, it is very simple, as you saw, that if you have three items, let's say you have item A1, item A2, and item A3, and you have four different types of features that you can provide to these items. So I'm doing exactly what was shown there. So B1, B2, B3, and B4 are the four different features. So let this be features and let this be items. and we can apply features to items. We are asking how many different possible three set of items are possible with different features. So how many ways we can assign features to this set of items so that where each item can access any of the four features independently of each other, of course. So what happens is A1 would be able to get all these four features, right? So it is free to choose any of this. So for A1, it gives you a 4. For A2, similarly, it will give you a 4. And for A3, it will give you a 4. And you simplify and multiply and you get 64. This is called the multiplication principle. For independent events, you multiply their number of possible outcomes to get the total possible outcomes for those two events happening simultaneously. So we want A1, A2, A3 to simultaneously have features, and we want to find out the total possible ways for that. That is why we did the multiplication principle. Now, if this were restricted, then again, if saying that A1 goes first, A2 goes second, and A3 goes third, so in starting, A1 will have four choices, and A1 is going to pick any one of them. Let's say one is only allowed. And after that, A2 is going to have three choices because A1 has already picked one. We do not know which one, but it does not matter. So A2 will have three choices. Similarly, A3 will have two choices. And this would give you 4 into 3 into 2, which is 4 into 3, 12, and 12 into 2, 24 different outcomes for A1, A2, A3. And this is when we do not allow repetition. Okay. So here repetition was allowed, here repetition was not allowed for features. The word mathematics, consider that it has two M's, two A's, and two T's. How many ways we can permute the word mathematics? Well, first of all, it has a total of 11 letters. We have to find out that, and then we have to find out all the possible duplicates. Now, the answer is simply 11 factorial upon 2 factorial, 2 factorial into factorial, which gives you, after simplification, the final answer. Let's see how to rearrange words. So we have seen the mathematics example, and now we are going to see the Mississippi example. So let's count the words: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 letters. Now, notice that there are 4 instances of only I's, 2 instances of P's, and 4 instances of S. So these are the repeated letters, and rest everything M is already in place, and which is only one in there is only one of them, right? So as you saw, in order to find out the total number of permutations of this kind of words, we use the multinomial coefficient, which is given by n factorial divided by n1 factorial, n2 factorial, n3 factorial, and all the way up to nk factorial, such that, very important, that n1 plus n2 plus all this nk, this would add up to n. This is important. So similarly, we will follow the same rule. We will write 11 factorial divided by 4 factorial, 2 factorial, and 4 factorial. And whatever this thing gives us will be our answer. I'm not going to calculate it. I do not really know the answer right now, but you can do it easily. But this is how you're going to solve any problem with rearrangement of words. Now let's look at an example and understand permutations with restrictions with an example of a gap problem. Consider arranging 3 boys and 4 girls in such a way that no 2 boys or 2 girls stand next to each other. So let's say the pink ones are our girls and the blue ones are our boys, and we want to ensure by swapping that no 2 boys or girls are adjacent. You can see we can start swapping the boys, and in that way, whenever they're alternate in position, they are not together, which satisfy the constraint, and we can also swap the girls amongst themselves. In order to do this mathematically and find out all possible combinations, we need to use logic here. So firstly, place all the 4 girls in a row, then place all the 3 boys in a gap between the girls. And in this way, we can find out how to permute. So number of ways to place for the 4 girls would be 4 factorial, which is 24. And number of ways to place the 3 boys would be 3 factorial, which is 6. And you simply multiply it because we have learned the multiplication principle. And this would give us 144. So let's talk about the gap problem that we have just discussed. So I will iterate a different version here. Let's say you have B, 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 and B. There's 5 boys here. So initially, let's say you had 5 boys and 4 girls, right? And you want to arrange them in such a way such that no 2 boys or no 2 girls are together. The way to do that, and this kind of problems are very common, I would say. So they would not directly maybe ask you to do that, but you have to understand from the statement how that is relevant and how that is to be done. And if you understand that okay, this is a gap problem, you need to apply this strategy. First, place all the items of the first kind, in this case, boys, in a row, and try and understand how to arrange them. So there are five distinct boys. We can arrange them in 5 factorial ways, correct? And now inside the gaps, how many gaps are there? You see one, two, three, four, five, and six. Right. But the thing is, there are only four girls, and we have to fill all these spaces, all these places, right? If there were more, we could have considered, but there are only four girls. So we cannot put in these two places, because if we were to put in any of these two places in the extreme, one of the places inside would have been empty, and then two boys would have come together, which is against the problem. So we need to permute four girls into these four places. How many ways to do that? 4 factorial. But is the answer? Answer would be simply 5 factorial into 4 factorial. Additional constraints may apply. If there are five girls, you need to understand how to choose four out of these five places, and then use 4 factorial to permute the girls. So these are gap problems. We will discuss about gap problems and PYQs for JEs and other examinations later on in another video. But for now, this would be enough to understand how the gap problems are working. Now look at these four boxes. How many ways we can arrange these four boxes by swapping so that none of the boxes go in their original places. This type of a problem is called derangement, and we're going to learn about it and its theory now. So as you saw in derangements, so derangements basically mean that you do not have the luxury to going back to the same place. And derangements dn usually is given by dn equals to n factorial, and then you have 1 by 1 factorial minus 1 by 2 factorial plus 1 by 3 factorial, and so on. Okay. Now, limit n tends to infinity, dn by n factorial is equals to E inverse. Okay, so this is a very important fact that is also sometimes used in limits, and you can prove it using your own identities, which I'm going to provide you right now. So I'm going to only say that e to the power x has an expansion of 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus x to the power 4 by 4 factorial, and it goes up to infinity. And this is true for all x belongs to real. That is, this function has a radius of convergence, which is the whole real numbers. That is all of real number. You can put in any value of x, and this series is always going to converge. Using this, try and prove that this limit n tends to infinity dn by n factorial is E inverse indeed. So dearrangements can be used in a lot of places, as you saw. If a man is there, and let's say he has 5 different routes to go to some place, and he chooses one to go to that place, right? How many ways can he go and come back so that he never takes the same road? That is one of the problems of derangement. And then you have the classic problem of derangements, where you have shuffling of cards. So all these problems will be discussed later on in separate videos, but this is an introduction video to permutations and combinations and its related principles.